Now we'll be doing a sample problem for the bolted connection topic. The problem here is shown in this figure. We have a bar that's connected to a gusset plate and it's in bolted connection. The bar is an equal leg angle, that's L152 by 152 by 9.5, and then the gusset plate is a it's an A36 12 mm plate, so the thickness is 12 mm. The bolts are A325 20 mm in diameter, and it says it's on standard bolt hole, and assume the threads are in shear. The distances we have here, we have the 40, 80, and 50, and here we have 35 from the center of this bolt hole to the edge of this bar. But with respect to the gusset plate, we have this distance 50 from this center to the edge of this gusset plate, and the center distance here is just 82. Okay, so the first step to do in an analysis type of problem is by the way, let's add a value here, uh, or let's add a problem. Determine if the details, if the bolted connection shown can safely carry a, let's say, a factored load of 300. Okay, so now the first step to do is to obtain the necessary information. Obtain the necessary information. Okay, so in our lecture handouts we have, for example, A36. If the steel is A36, the FU, the ultimate tensile strength, is 400 megapascals. The um, the shear strength, so the A325, the shear strength is, we should refer to, see, table 13-2, and we have to check the description of the fasteners, and we have to find the A325 and threads in shear, meaning threads are not excluded. So that's going to be the third row in the table. We have a value of 330 megapascals. And the next one is the diameter of the bolt hole. So for this, we have to refer to the table, this is table 13-4, and since we have a bolt of M20, and therefore our standard size is 22 mm, and the area of the bolt can also, I think we can obtain this from another table, but we can also solve that. Pi d squared all over 4, that's all over 4, and that's going to be 314 mm squared. Okay, so now let's solve for the bolt shear capacity. Solving for bolt shear capacity. Okay, so our factored shear, R sub n, is equal to the reduction factor times the shear strength, the nominal shear strength of the bolt, and V times the um, area of the bolt. To take note, for now um, we are just writing or calculating the shear strength or the shear capacity of a single bolt only. So if we have 4 bolts over here, then we have to multiply that by the number of the bolts. Okay, so let's substitute the values. We have 0.75 times 330 megapascals times the area of the bolt, which is 314. Okay, this is 0.16. That's mm squared. Okay, so we have 77.75 kilonewtons. Now for 4 bolts, we have VRN is just 77.75 kilonewton times 4, since we have 4 bolts. So we get here 466.5 kilonewtons. Okay, so now the next step is to solve for the bolt bearing capacity. Okay, so recall that bolt bearing is actually independent of the type of fastener, but it's actually the plate material. So it could happen that bearing can happen in this tension bar, or is it also possible that the bearing can be on this gusset plate? So we have to check the bearing capacity of this bar. Then later we'll also check the bearing capacity of the plate. Okay, so for now, let's say bearing capacity of the tension bar. Okay, so for the first step, before we can actually apply the equation of the bearing capacity, we first have to determine the clear distance. Okay, so let's write here, determine the clear distance. Okay, so first we have to sketch this bar. And the distance between this, the center to center distance, and this the distance from this center to the edge, this is what we call the LE, and that's the exterior, and this one is the LI. Now LE is 40 while LI is 80. Okay, so let's say 40 mm, and this one is 80. Okay, what else? So this bolt diameter bolt hole diameter is, this is 22 mm. Okay, so let's write it here. Bolt hole diameter is equal to 22 mm. So meaning the clear distance is either this one or this one. So we have to check whichever is the minimum. Okay, so first the equation is L sub C is equal to the minimum of the two condition, which is LE minus dH over 2, and another condition is Li minus the diameter of the bolt. So it just means that whichever is the minimum between the two, then that's going to be our LC. Okay, then next we'll substitute the values of the LE and the DH. What you get is 40 minus 22 all over 2, then 80 minus 22. So we actually have say minimum of 29 or 58, and the minimum is 29. Okay, so this is our L sub C. By the way, let's label this, let's say figure 1. So meaning we can relate this or reference this. Let's say C figure 1. Okay, so the next step is to solve for the bearing capacity. Okay, so this is B. Solving now for the bearing capacity. Okay, of a single bolt. So Rn is equal to 1.2 times T. This is our equation times the minimum of either LC or the 2 times the bar diameter. Okay, so we substitute the values. We have 1.2 times the thickness. Now this thickness refers to the thickness of the bar, and it's actually can be obtained from this given value. This is the width of the leg of the angle bar, and this is the width of another leg. This is the thickness. So that's 9.5 mm, and the ultimate tensile strength is 400 megapascal. Okay, times the minimum of LC, and that's 29, and 2 times the bolt diameter. Our bolt diameter is 20 mm, so 2 times 20, that's gonna be 40. Okay, so if you do the math, what you get is 132.24 kilonewtons. Now, solving for the capacity of the 4 bolts, we have V Rn is just simply Rn times the number of bolts. Of course, we have to multiply that to the reduction factor times the let's say NB. So that's gonna be 0.75 times the Rn, 132.24 kilonewton times 4. That's that's going to be 396.72 kilonewtons. Okay, so that's going to be our um, our apparent capacity of the bar. Now let's solve for solving for the bearing capacity of the plate. Okay, so for this we have to draw again our plate, and our distances here we have 50, and this one is 80, this one is 50, and this one is 82. So let's say this is our figure 2. Okay, so we can write it here, C figure 2. Okay, so now we have to solve for the LC. Okay, so LC is equal to the minimum of the distance, the edge distance, minus diameter of hole over 2, or the interior distance minus the diameter of hole. Okay, so if we substitute the values, we have this one is 50 minus the diameter of the bolt hole, 22 over 2, and this one is 80 minus the diameter of the hole. That's gonna be minimum of either 39 or 58. So we have this value, 39. Okay, so now we can now solve for the bearing capacity. So let's say solving for bearing capacity. Okay, so Rn is equal to 1.2 times T times this one times the minimum of either LC or 2 diameter of the bolt. Okay, so 1.2 times the thickness. Now this thickness refers to the thickness of the plate, which is 12 mm, times 400 and the minimum. By the way, in our bar, I didn't specify if it's A36 or not, so let's just write here it's A36, so that we can use the this ultimate tensile strength of 400 megapascals. Okay, so this will be minimum of either 29, 39. That's 39 or 40. Okay, so we have 224.64 kilonewtons. Okay, so the factored capacity of bolted connection is VRN is equal to the reduction factor of 0.75 times this value 224.64 times the number of bolts. That's going to be 673.92 kilonewton. Okay, so the next one is to check. So checking minimum requirements. Okay, so let's check first for the maximum spacing. Now it says as mean is preferably equal to 3 times the bolt diameter. So that's 3 times 20. That's going to be 60. For the S max is now let's assume that the connection is subjected to atmospheric corrosion. So we have an S max of 14T or 180 mm. I think this should be the minimum. Okay, so minimum 14T. Now the thickness should be the smallest thickness between the two, either the thickness of the bar or the plate, but the bar has 9.5 while the plate is 12 mm thick. So this one should be 14 times the 9.5 or 180. Okay, so 14 times 9.5, that's 133. So therefore our X maximum is 133 mm. Now our spacing is, so our spacing here is actually 80. So meaning our S, this is S mean, is greater than our S mean, and this one is greater than our S max. Therefore, code requirement is met. Code requirement is met. Okay, for the edge, minimum and maximum edge spacing, I think we'll just write it here. Okay, so this is not number 6. We're still in the minimum requirements. Then for our LE mean is, if we can obtain that from table 13-5, and we have a value of 26 mm. Okay, and the next one is the maximum distance is the minimum of either 12 times the bar diameter or 150 mm, and we get a value of 114 mm. Now our edge distance is, our LE is greater than our minimum. So this is the minimum, this is our LE, our edge distance. I guess we have either 35 or I think this should be in relation to this load direction. That's gonna be 40. So 40, and it's greater than this maximum LE max. Okay, so therefore code requirement is met. Okay, so now let's check the summary. So in summary, we have the shear strength of bolt, which is 466. VRN is equal to 466.5 kilonewtons, and then the bearing capacity of the plate, that's 396.72, and then another bearing capacity, but that's the bearing capacity of the gusset plate. This one is the bar, and that's 673.92 kilonewtons. Okay, so our governing capacity would be the minimum of the three. So therefore, VRN is equal to 396.72 kilonewton, and VRN is greater than our factored loads. 396.72 is greater than the given load of 300. Kilonewton. Okay, so in review, this is our problem. Actually, this is an analysis type of problem, because if it's a design problem, then we are to determine the number of bolts and the geometry. But here we're actually given this geometry and details, and we just have to analyze. Okay, so the first step that we did is to obtain the necessary information from the tables, from the steel tables. For example, the ultimate tensile strength, the diameter of hole. Of course, you're given a bolt diameter, then you can actually determine the diameter of bolt hole, then the area of bolt. And once you have that, then we start solving the capacity. Now, actually, you can solve first the bearing capacity if you like, but us here, we solve first the shear capacity of the bolt. So we apply the equation, then we substitute all the values. Take note, this equation is only true for a single bolt, and we still have to multiply it to the number of bolts. Okay, so let's say number of bolts, then that's gonna be the capacity. And then the next step that we did is to solve for the bolt bearing capacity of the tension bar. So take note that the bearing capacity could either be the bearing at the plate, the gusset plate, or it can be bearing in this tension bar. So we have to check the two. Okay, so the first step in determining the capacity, the bearing capacity, is to find the clear distance, the governing clear distance. So that's the distance right here. So whichever is the smallest, then that's the one governing the equations. Okay, so you obtain a value of 29. So after that, we solve now for the bearing capacity of a single bolt, and we just apply the equation, then we multiply that to the number of bolts, and you get this. The next step is to solve for the bearing capacity of the plate, and we did the same procedure, and we solve for this clear distance. And once we have obtained the clear distance, then we can actually solve for the bearing capacity. That's 22.64, and if we multiply that to the number of bolts and the reduction factor, then we get 673.92. The last step that we did is to check for the minimum requirements, especially the minimum and maximum spacing, and this edge distance. Okay, that's the edge distance, the minimum and the maximum edge distance. So for this, the minimum is just simply 3 times the diameter of the bolt. that's 60. The maximum, that depends if we have a condition wherein the connection is subjected to corrosion, or if it's painted or not. Okay, so we just assume the worst case condition, and this is it. This is our equation, and the thickness here would be by the way, with regard to the thickness here, I'm not yet sure if it's gonna be the thickness of both the plate and the bar, but if that's the case, then you have let's say a larger value, but it just says that that's gonna be the thickness of a part only. Okay, so let's assume for now in this homework that that's gonna be the thickness of these. Let's say the part wherein we have a minimum thickness, so either 9.5 or the 12 mm. Okay, so we solve that, and we obtain a 133 millimeters. Now notice, if you include the thickness of both the plates and the bar, then you'll actually obtaining a larger value here, and probably what's governing is this 180. Okay, so but still our S spacing is within the minimum and the maximum range, and therefore the code requirement is met. Then we solve this edge distance, so use the tables, and then we solve this the maximum, we compare. Now in summary, the governing capacity would be the minimum of the three capacities. That's the bolt, shear, and the bearing capacities, and we compare that to the applied load, which is 300 kilonewtons. So since it's greater, then it's okay. Now we didn't consider the tension capacity, since this is just a bearing nut connection. All right, so I guess this will be the only sample problem that we have for the bolted connection, since it's just pretty straightforward if we just do analysis. But for a design problem, then that's gonna be a different approach, or method for a calculation. Okay, so in the next video we will consider the welded connection.